and naive Bayes classifier. The naive Bayesian classifier relies on Bayes' theorem with the independence assumptions between predictors. A naive Bayesian model is simple to create with no complicated repetitive parameter estimation. This makes it helpful for massive datasets. Despite its simplicity, the naive theorem classifier typically does amazingly well and is widely used because it outperforms other sophisticated classification models. Bayes' theorem provides a way of calculating the posterior probability P-A-B from P-A-P-B and P-B-A. Naive Bayes classifier assumes that the effect of the value of the predictor X on a given class A is independent of the values of other predictors. This assumption is called class conditional independence, where P-A-B is the posterior probability of class target given predictor attribute. P-A is the prior probability of class. P-B-A is the likelihood, which is the probability of predictor given class. P-B is the prior probability of predictor. Note, naive Bayes classifier assumes that the presence of a particular feature in a class is unrelated to the presence of any other feature. Steps to calculate posterior probability, Part A. The posterior probability can be calculated by first constructing a frequency table for each attribute against the target and then transforming the frequency tables to likelihood tables and finally using the naive Bayesian equation to calculate the posterior probability for each class. The class with the highest posterior probability is the outcome of prediction. The first step is to build the frequency table for each attribute against the target. The next step is building likelihood tables. As you can see from the likelihood table, we have all the required data to calculate the posterior probability. Probability of Sunny to be yes is equal to 3/9, that is 0.33. This is obtained by calculating the probability of predictor with respect to class. Prior probability of sunny weather is calculated with respect to the total probable possibility in class, that is 5/14, that is in return 0.36. Prior probability of class to be yes is 10/14, which is 0.71. Similarly, posterior probability class no given predictor sunny is the probability of sunny to be no, multiplied by probability of no with respect to total probable possibility divided by prior probability of sunny weather, that is 0.4 times 0.36 divided by 0.36 equals 0.40. Steps to calculate posterior probability, Part B. Similar to how we calculated the posterior probability for predictor sunny, calculate posterior probability for each of the other features. From the likelihood table for humidity, probability of high humidity is P, yes high, equals 0.33 times 0.6 divided by 0.5 equals 0.42. Probability of not having high humidity is P no high equals 0.8 times 0.36 divided by 0.5 equals 0.58. From likelihood table for wind, probability of weak wind flow is P, yes weak, equals 0.67 times 0.64 divided by 0.57 equals 0.75. Probability of strong wind flow is P, no, weak, equals 0.4 times 0.36 divided by 0.57 equals 0.25. Now let's calculate the output by first calculating the likelihood of yes overall. Likelihood of yes equals P outlook equals rain yes times P humidity equals high yes times P wind equals weak yes times P yes equals 2/9 times 3/9 times 6/9 times 9/14 equals 0.0199. Then calculating the likelihood of no overall. Likelihood of no equals P outlook equals rain no times P humidity equals high no times P wind equals weak no times P no equals 2 over 5 times 4 over 5 times 2 over 5 times 5 over 14 equals 0.0166. As you now know, the likelihood of yes and no, calculate the probability of yes and no, and then normalize the values. So the model predicts that there is a 55% chance that there will be game tomorrow. Support vector machines, linear separability. Linear separability